Earlier we have seen some application of angular momentum forces acting and the devices that where those computation calculations can be applied. So continuing with the same, we now try to do an example and we try to calculate the amount of fluid flow that takes place at certain points, that is outlet or inlet, as a result of the angular forces that are taking place or that are being forced. So here is one example, and we look at it. We try to work out the parameters and the variables that are involved. Underground water is pumped through a 10 centimeter diameter pipe that consists of a 2 meter long vertical and 1 meter long horizontal section. This has been shown in a diagram, and I have said it many times. This is taken from the textbook that we are following. Water discharges to the atmospheric air at an average velocity of 3 meters per second. So we need to note down, as this is the given data, and from this we have to do the calculations. And the mass of horizontal pipe section when filled with the water is 12 kilogram per meter length. The pipe is anchored on the ground by a concrete base. Determine the bending moment. So we need to calculate the moment acting at the base of the pipe, the point A, and the acquired length of the horizontal section that would make the moment at point A equal to 0. So that is the question. And when they try to draw the diagram that they have mentioned in the question, that this is an L-shaped diagram, and you can see the fluid sucked here, thrown out of this length. This much pipe is 2 meter long as given in the question. This data is from the question. So it's a 2 meter long, this part, and then 1 meter wide as we see it. The diameter here of this part of the pipe is 10 centimeter, and whereas the fluid that is going out is being thrown at 3 meters per second. So that is the basic picture, and then to be able to apply the equations that we have, and in terms of the variables that we can use, we try to see the radius. We have to look for things like the radius, the velocity, the mass, and so on, which are partially they have been given and some we have to find out. So the value of R is also given to us. R2 is here. Weight we have to find out, it will be mg, and the coordinates are taken as usual. The horizontal coordinate is taken to be as the direction x, and the vertical coordinate is taken to be as the direction of z or z, whatever you may like to call. The fluid rate going out is m dot v2, that is the velocity at this point times the rate of change of mass that is being thrown out. And Fr is the resultant force that is acting here, and that needs to be calculated. So when we try to consider this physical situation, physical parameters, we take the whole L-shaped pipe as the whole control volume, and within that we apply the forces. And inlet we consider as point 1 and outlet as point 2. Then we also take the x and z coordinates as shown. As I mentioned, the x direction, the horizontal direction is in the x direction, and the vertical one is taken to be as the z direction. The conservation of mass equation, the continuity equation, demands that the fluid coming in should be equal to the fluid that is going out. So therefore, m1, the rate of change of fluid at the entry point, should be equal to the fluid that is being thrown out, and let that be denoted by just m dot, rate of change of m. And this, the suffixes here has been removed. Similarly, the velocities at point 1 and 2 are equal, and therefore let that also be denoted by V. And the area of cross section C is constant, so it's denoted by AC. With these values, we try to calculate m dot with the given numbers that we have been given in the question. So substituting those values, we obtain m dot mass to be equal to rate of change of mass to be equal to 23.56 kilogram per second, and weight therefore as usual, which is equal to mass into gravity, acceleration due to gravity. And when we substitute those values, we obtain that W is equal to 117.7 Newton. To determine the moment acting on the pipe at point 2, we make use of this equation, and R is the average moment arm and V is the average velocity or speed. The free body diagram of the L-shaped pipe as given, and we note that the forces and momentum flows pass through the point A that are equal to 0. The only force that yields a moment about A is the weight. All other forces, their resultant is 0, and therefore weight is the only thing that has some contribution. And for weight, we have already calculated it, and when we make it substitution, then we obtain that the moment at A is 82.5 Newton per meter, and we happen to have a negative sign appearing in our answer. The negative sign is only indicating that the assumed direction of MA was wrong, and in fact the motion was taken in the reverse direction. So from counterclockwise, it should be considered in the clockwise direction. And that's all there is to it. So similarly, the other small terms that we have to calculate, they are all given in the question, and some we have computed, and therefore their result can also be computed. It's just a matter of computation, just substituting the values that we have, and a simple arithmetic gives you this result.